What is the meaning? Simple bending or the pure bending? Theory of simple bending or pure bending. To understand this theory of simple bending or the pure bending, let us consider an example of a beam. Let me write a figure of a beam. I'll provide two simple supports at end A and B of the beam. And I will divide this beam into three equal parts or three equal lengths. Here L by 3, L by 3 and L by 3. If we take L as total length of the beam. Okay. Now I'll apply two loads at 1/3 portion of the beam. Here I'll apply a force of W by 2, and at this point also I'll apply the same force W by 2. Let me consider these points as point C and point D. Okay. Now for this beam we will develop shear force and the bending moment diagram. So here I'll take reaction as RA, simple support, RA in y direction and RB in y direction. First we'll find the support reactions. See, if you find support reactions at A and B, you will get RAY is equal to RBY is equal to W by 2 only. So here whatever the loading we have applied, it is symmetric loading. Therefore, whatever the total load that will act on the beam, it will be equally divided to the both the supports, so that the supports will generate reactions of equal magnitude. That is why the total load which is acting on the beam is W by 2 plus W by 2. Total W is the total load acting, divided by 2 means again W by 2. So the reaction is RAY is equal to RBY is equal to W by 2. Otherwise, we can find the reactions by applying equilibrium equations. Because of symmetric loading, I have directly written the answer. Now let me find the shear force at each and every point. Shear force. Shear force. shear force at A is equal to shear force at A is equal to, it is W by 2. Here we have the reaction as W by 2 and RB by W by 2. So whatever the reaction we have, that is only the shear force at A. And shear force at C. Shear force at C is equal to minus plus WL by 2 minus WL by 2 plus W by 2 and minus W by 2, which gives 0. Zero shear force at C. Similarly, shear force at D will be equal to shear force at D is equal to 0 minus W by 2. Means previous value 0 minus W by 2. So we'll get minus W by 2. And shear force at last point is again shear force at B is also W by 2. Means minus W by 2 minus W by 2. So at the last point, I will take the shear force with the negative sign. Because the right portion of the beam is tending to uh, cause upward motion of the beam. That is why as per the sign convention of the shear force, so negative sign will come at the last point, of the beam. Similarly, if you find bending moment values, bending moment at A is equal to 0 because it is simple support. At simple support, there will not be any moment. Therefore, bending moment at A equal to 0. Then bending moment at C will be equal to bending moment at C is equal to W by 2 into L by 3. W by 2 into L by 3, you will get WL by 6. And bending moment at next point D is equal to, at D is equal to, you find bending moment of reaction about point D, that is W by 2 into L by 3 plus L by 3. W by 2 into L by 3 plus L by 3 is the perpendicular distance of this reaction W by 2 about point D. The moment of this W by 2, which is acting at point C about point D, is equal to W by 2 into L by 3 minus W by 2 into L by 3. So negative sign is because this force acting at point C will cause anti-clockwise moment about point D. That is a minus sign, and this reaction W by 2 at A will cause clockwise moment about point A. That is why here it will be plus sign. If we simplify this equation, here W by 2 into 2L by 3 minus WL by 6. Here 2 gets cancelled. Finally, it is WL by 3 minus WL by 6. It will be 2WL minus WL. You will get the answer as WL by 6. Bending moment at D. And bending moment at B, last point of the beam. Again it will be 0 because simple support is there. At simple support there will not be any moment induced. Therefore bending moment at B is 0. If required, even if we calculate moment from support A, moment each and moment of each and every forces about uh, point B, and you add up all the moments, you will get 0 only. So I'll directly write the answer as 0. Bending moment at B equal to 0. B equal to 0. So if I draw a shear force diagram, shear force at A is W by 2. W by 2. And shear force at C is 0. Shear force at C is 0. And shear force at D is minus W by 2. Minus W by 2. And shear force at B is also minus W by 2. If I draw shear force diagram, it will be like this. This is the shear force diagram, SFT. So here the nature of shear force is positive. Here nature of shear force is negative. And if I draw bending moment diagram, bending moment diagram will be bending moment at A is 0 and bending moment at C is WL by 6 and D is WL by 6. Same value at C and D. At point C and D, we have WL by 6 as bending moment, and at point D also WL by 6 is the bending moment, and at last point at point B, bending moment is 0. Now the BMD will be so this is the bending moment diagram. Nature of bending moment diagram is positive here. Here you can observe one thing. For this particular loading condition, when you observe shear force diagram, shear force between points C and D is 0. Shear force between points C and D is 0, but we have bending moment between C and D. Therefore, the pure bending is nothing but if a beam is subjected to only the bending moment and the shear force at that particular span is 0, then beam is said to be, or the part of the beam is said to be under pure bending or in pure bending condition. Okay, so therefore the pure bending is a bending where the shear force is 0 for a specific length of the beam and there will be only bending moment which acts on the beam, that is called as pure bending or the simple bending. Okay, and whatever the stresses developed in pure bending of the beam, those stresses are called as bending stresses. Those stresses are called as bending stresses. Okay, so whatever the stresses induced in the beam due to bending of the beam are called as bending stresses. If I take a simply supported beam or bending pattern of the simply supported beam, this is the bending pattern of the simply supported beam. Okay. Now, if you observe the bending pattern of the beam, here you can see the bottommost fiber of the beam is subjected to tensile stresses and topmost fiber of the beam is subjected to compressive stresses. Means there is increase in length of the bottom fiber and there is decrease in length of the top fiber, or there is tensile force acting in the bottom fiber, there is compression in the top fiber. If I take the fiber which is very next to the bottom fiber, again that fiber is also subjected to tensile stresses. If you go on taking fibers one above the other from the bottom fiber, the tensile stress goes on decreases. Tensile stress goes on decreases. At one particular point, there will not be any tensile stresses or the compressive stresses. If I take the fiber which is very next to the top fiber, there will be compressive stress in this fiber, but relatively lesser compressive stress when you take the compressive stress in the topmost fiber. Similarly, if you take the next fiber, in this fiber, comparatively less compressive stress compared to the previous fibers, like this. The compressive stress also goes on decreases. Compressive stress also goes on decreases, but at one particular point, the compressive stress will be 0, as well as the tensile stress will also be 0. The fiber at which both compressive stresses and tensile stresses are 0 is called as, or the axis at which the compressive stress and the tensile stress in the beam are 0 is called as neutral axis. Is called as neutral axis. Okay, this is about the bending stresses. Now, in this video, we have learned about the theory of simple bending or the pure bending, and we understood the meaning of bending stresses and the nature of stresses developed in the beam, and we have also understood about the neutral axis. Thank you.